should start.
Sure.
So I'll give you 5 minutes, I guess. Actually, so we finish on time.
Yep. So it's supposed to finish at 2:50 or 3?
2:50 and
Okay.
questions. Yeah.
Sure.
Because it starts again at 3, right?
Yep.
Okay. So our speaker this afternoon is William Stein, coming from the University of Washington, Department of Mathematics. He got there via Berkeley, where he got his PhD, and then spent a few years at Harvard as the Benjamin Pierce Assistant Professor of Mathematics. Was Associate Professor of Mathematics at the University of California, San Diego, which is what it says in the program, if I'm not mistaken.
I got invited to this when I was still there.
And the title of his talk is SAGE, Open Source Mathematics Software. If you Google SAGE on the web, you'll find out that I believe it used to stand for a computer system for algebra, geometry, experimentation, but it's, as I think we'll find out, can do far more than that these days. Let me just say a little bit about open source. We all know successful commercial packages like Mathematica and MATLAB, and it's nice to see them. They were founded by mathematicians or run by mathematicians and hire a lot of mathematicians. But I think it's even nicer and more impressive to see the mathematical community itself put together something as sophisticated and capable as SAGE through the open source, kind of open collaborative development model, maybe a minimal amount of funding, and then especially the leadership of our speaker, William Stein.
Okay, thank you for that nice introduction and for the invitation. So I'm going to basically answer the question, what is SAGE, and show you a little demo of SAGE, and then just give you some sense of the historical perspective. But I think it's sort of evolved over time. That on the left I've written kind of a fairly technical description of what SAGE is in the sense that I actually say something. But the kind of just thing to take away in your mind is, as you said a moment ago, everybody's aware of a lot of situations where there's a sort of very commonly used famous piece of commercial software, and then a corresponding open source program that's developed in a more grassroots way, if you like. And here's some examples: Firefox and Internet Explorer, Microsoft Windows, and Linux, the Apache web server, and IIS, et cetera, et cetera. The whole bunch of examples like this. And my hope is that one day SAGE will kind of fit into this picture. Where over here you have Maple, Mathematica, MATLAB, and Magma. So in one sentence, the goal for SAGE is to provide a viable alternative to these commercial systems in the same way that Firefox is a viable alternative to Internet Explorer, and to really provide an alternative to all 4 of them, and to do so in a very open, sort of grassroots way. And now I'll tell you a lot more. So, so here's kind of a quick abstract. And basically, I want to explain to you how Python and SAGE can improve your efficiency and ability to do math research in ways that should be very helpful to you. And I'm really aiming this talk at mathematical researchers who really want to have the best possible tools. The audience for SAGE, I think, is much larger, students in classes and so on, but this talk is targeted at research mathematicians. Here's a historical perspective on SAGE and also my involvement in software. As was mentioned in the introduction, I was a grad student at Berkeley, and I wrote a lot of C++ code. And then right near the end of my time at Berkeley, I discovered Magma and wrote quite a lot of Magma code. I visited them 3 times in Sydney, Australia, and wrote a lot of functionality for modular forms and abelian varieties and so on. Things that were related to my thesis research. But after using Magma for very, very, very seriously for about 6 years and trying to convince everybody I knew to use Magma as well. Magma, by the way, is a commercial program developed at the University of Sydney in Australia. And it has a fairly small user base, maybe only a few thousand people total. Since it's aimed at really group theory and arithmetic geometry and number theory and coding theory, it has a very, very clearly targeted audience, which is different than most math software. But these languages, the language that Magma has, you can't define your own types, you can't, the garbage collection is extremely basic. There's just a lot of issues with how scope works. It just isn't, I mean, it's a language that was designed in the early 90s, didn't really change much since then, and it was designed by mathematicians, which, I mean, we're really good at a lot of things, but I'm not sure that programming languages are necessarily, or at least general purpose programming languages, are what we do the best. So there are more modern languages like Python that do a lot of things right, they're more pleasant to use, and they've been tested in a much wider range of applications than, say, the language Magma or Mathematica or Maple. Also, I noticed that I really needed to be able to see inside of software in order to be the best possible at a given area. I mean, at the end of the day, I have problems that I want to solve. I need to get data about those problems, and I have to be able to do things absolutely optimally, or somebody else will do it better, or whatever. And I'll be very frustrated. And with closed source software, it's just not possible for me to dive in at any point, anywhere in the software, and change anything I need to in order to really push the envelope. Like, basically, when I do computational stuff, it isn't just playing around with some integrals or something. It's really using algorithms that are, right at the edge of what we can do, optimized as much as possible. And if you're not doing that, then you're not really kind of pushing the envelope. So I was frustrated with Magma, and I decided about in 2004 that it was really a terrible long-term investment to be putting so much energy into developing for Magma when it's a closed source program, and much more importantly, the development model is very closed. There's one guy who decides what goes in, decides what doesn't go in, and his decision process is completely opaque. So it's frustrating. And it's mostly frustrating when he decides that something you do shouldn't go in and just says no. So in February 2005, I released the first version of Sage. I sort of experimented with a whole bunch of possible languages, libraries, and so on during the previous year, but then I finally made something which I showed to other people. And actually the first release, I was sitting at the AMS winter meeting in Washington, DC 3 years ago, or 2.5 years ago or whatever, at a table, sort of hacking on some code, and then some person walked by who I didn't know, but who knew me, and started talking to me and asked what I was doing. And basically that conversation led to me making a release. It turned out the guy was David Joyner, but I pretended like I knew him, but I didn't actually know him. So a year passed, and David Joyner, me, and David Cole, who worked a lot on Magma also, wrote a large amount of code for Sage and sort of got Sage going just amongst ourselves. And then after 1 year, I ran a workshop at UCSD. And I had no idea what the reception would be like. Did people think that creating something like Sage is sort of stupid, or was it a good idea? I really had no idea what to expect. But in fact, across the board, the people at the workshop were incredibly enthusiastic about Sage. It seemed to clearly be filling a desire that a lot of people had. So that was very nice. And subsequently, I've run actually 4 additional workshops on Sage. These are mostly Sage developer workshops. So a bunch of people come in, usually about 30, and there are a couple of talks and a lot of coding sprints where people get together and try to design things, and they argue about how p-adics should be implemented, and then spend a huge amount of time coding up p-adics and so on, intermixed with a lot of talks. The last workshop was actually just 2 weeks ago at the Clay Math Institute in Cambridge, Massachusetts. And that workshop was interesting because it was focused on computational arithmetic geometry. But it still involved a large amount of Sage, implementation of arithmetic geometry, algorithms in Sage, and so on. There'll be a workshop basically focused on cryptography using Sage and developing basic tools for cryptography in Sage in Bristol at the Heilbronn Institute pretty soon. So that's kind of a brief history of Sage. It started in 2005, and now it's 2.5 years later. And so Sage is it's basically what you get when you take Python, which is this very modern programming language, and then you take really all the best reasonably buildable open source math software, put it all together, and then do several years of work by about 100 people to make it all work together smoothly. That's what Sage is. So let me tell you a little bit about Python in case you don't know. How many people here have ever actually used Python for anything? Okay, so like 4 or 5. How many people have used a program written in Python? Like maybe BitTorrent or something, which was written in Python. Cool, so some people. So here's Python. How many people have used a website that uses Python behind the scenes, such as YouTube or Google, or watched a movie that was rendered using or watched a movie that was rendered using Python as the sort of glue that binds it together? So here are a couple of quotes from one of the YouTube people. Python is fast enough for our site and allows us to produce maintainable features in record time. Google's made no secret of the fact they use Python a lot for a number of internal projects. Even knowing that once I was an employee, I was amazed at how much Python code there actually is in the Google Search Control System. So that's a quote by Guido van Rossum, a Dutch person who created Python about 15 years ago initially.
Was he a math PhD student?
Maybe. He's definitely not a mathematician. I think he may have an undergrad degree in math, maybe a master's degree, but he's really computer science.
Yeah.
I talked to him and it became clear that he does not view himself as a mathematician, which is fine. He's a computer guy. Another quote, Python plays a key role in our production pipeline. Without it, a project the size of Star Wars would have been very difficult to pull off, etc. So Python's something that makes it possible to pull off large projects like Star Wars Episode 2 and Sage, as you'll see in a second. A few more words about Python. It's a nice modern language. It's easy to define your own data types. You can make a bitstream data type or a ring data type or whatever. It's a clean, easy to read language. And actually that's one of probably the most important reasons why I chose Python for the Sage project was that I knew that in the long run there would have to be a large number of developers to do this. What I want is a viable alternative to these systems. And if you look, say at the Mathematica website, they say that they have they're a closely knit group of 550 employees. And you have to, in order to even begin to compete with that, given how far behind we are at the start, you need a large number of developers, and you have to be able to easily read each other's code. And that has actually turned out to be the case very much with Sage. Python itself is pretty easy to read. Easy to learn. There are a couple of books on Python that are free. One of the most important things about Python is there's a huge number of third-party libraries available for the language. Some of which have absolutely nothing to do with mathematics, but for which it's nice to be able to combine them with math. Statistics, of course, involves math, but there's a lot of support for networking, like running a web server, databases, physics, video games, 3D graphics, numerical computation, all kinds of things. And it's also easy to use existing libraries from Python, Fortran libraries, C libraries, and so on. And it has good support for string manipulation, which is something that's often lacking from math software. Finally, very, very importantly, there's a Python compiler which turns interpreted Python code into C code, which you then compile, and it is faster. And this is incredibly important. It's really completely impossible to make a really, really fast system if you just use an interpreter. In fact, probably a third of the new code we've written for Sage is written for this compiled variant of Python. And one thing that's been very lucky is my grad student happens to also be incredibly good at compilers, so he's put a lot of work into improving this compiler, making it much, much faster and much more full-featured. So it's actually become a pretty interesting project in and of itself. It's called Cython. So, you're here to hear about Sage, not Python, so let me tell you a little bit. So here's an example of using Sage, and I'll show you more. Oops, make sure that, there. So you type Sage at the command prompt, and you wait a little while, and you will see the Sage prompt. There we are. And it can do various calculations, just like any other math software you use too, except in some ways it's better, and in other ways it's not. You can do things like sine of x squared. So right here what it's doing is it's taking a while because it's starting up a copy of the computer algebra system Maxima, and it's amazing this is taking time. And I'm running this in a really, it's starting, so the first time you do it, it's slow. It does that because it wants to do various simplifications, so So it simplifies the results. The first time I type an expression that involves symbolic objects, it starts up one copy of the Maxima computer algebra system in the background. Maxima is actually one of the first computer algebra systems. It was developed initially in the late 60s and early 70s at MIT. And it plays a key role in SAGE. One of the sort of slogans of SAGE is building the car, not reinventing the wheel. So for symbolic integration, differentiation, Taylor series, all this sort of thing, we just took Maxima. Then an undergrad spent about a year writing a very nice Python interface to Maxima. And that's kind of what you're seeing right here. You can type in things like this. You can do integrate the sine of x squared with respect to x. Computes the integral. We didn't write any symbolic integration code for SAGE. We just feed the question to Maxima and get back the answer. That happened behind the scenes right then. So this is an example of SAGE. There's also a GUI interface to SAGE, which I'm going to use in a minute or two, or actually probably about 10 or 15 minutes for the demo. You start the GUI interface for SAGE, the graphical interface, by typing go. And I will show that to you later. The command line, though, by the way, is actually very, very nice compared to your average command line. So if I quit SAGE completely and then restart, you'll notice that the history is persistent, which is nice. Also, you can do reverse search through the history. So if I type IN up, then I get lines that begin with that at the beginning. So notice also that starting at Maxima that time was much faster. It's just that I hadn't started things in a long time. That's why it was slow. Okay, so back to the talk. There is a graphical interface which I'll show you live in a minute. This is kind of a little snippet of it. It's actually a very powerful graphical interface because it's written as a web server that you connect to using a web browser. So you can start up the part of SAGE that does all the calculations on a computer, say in Seattle, and then the graphical interface you can just have right here. That sort of thing works. It has kind of a modern feel. It feels a lot like a Mathematica notebook or something. You have embedded graphics. You can typeset mathematical expressions. You can, you can insert new input wherever you want. You can start a whole bunch of calculations at once, kind of queue them up. And an interesting thing, we designed the notebook to be very open, so you can actually switch it to be a Mathematica notebook or Magma notebook or an Octave notebook or whatever. It's not just a SAGE notebook, as you'll see. Okay, here's a little bit about the amount of code and the sort of things that SAGE is built out of. So I'll flip this on for a second. So SAGE, if you wonder after the talk's over, what is SAGE? The answer is it's a distribution of a whole bunch of open source math software. And I'm going to go over a little bit of what open source math software is included in SAGE in just a second. So in and of itself, that was a very interesting problem. How do you make it so it's trivial for anybody to install all that sort of open source math software on their computer? Or even harder, for certain people who are really trying to do cutting edge research, you want it so that they can build the entire thing from source code. Because it's critical that they be able to change anything in the whole system. So we did solve that problem, I think, through a lot of work with a lot of different people. So we have kind of a complete tarball that when you extract it and type make, it'll build everything that's listed there and a lot more. Second, SAGE is a large amount of new code, as I've mentioned before. We wrote a lot. We wrote, for example, the graphical interface that you see. We wrote code for computing with elliptic curves and modular forms, some of which isn't available in any other software, etc. We also have interfaces to other software. So you could have, say, a program you wrote in Mathematica, and if you have Mathematica on your computer, then you can call that a function that's in Mathematica. And I'll give you a little example of that in a minute. So let me quickly go over this list. So this is a list of some things that are in SAGE. For algebra and calculus, Maxima is really the engine that does most of the work. There's also a program called SymPy, which is written in pure Python for symbolic computation, and it's developing very rapidly. For example, the SymPy project, which is led by I think a Polish undergrad, got $25,000 in support from Google last summer for development. So that's a piece of SAGE, and it benefits us. There are several libraries that we've really smoothed out and integrated into SAGE that support arbitrary precision arithmetic. Of course, GMP, but also MPFR for real number arithmetic, MPFI for interval arithmetic. The interval arithmetic stuff is very interesting. The guy who maintains the code that makes it easy to use MPFI within SAGE is an engineer at a company that does computer vision. So he just sort of showed up on the SAGE Minidus one day and suddenly started contributing large amounts of really, really, really good quality code as a hobby. You know, we invite him up to give talks, and he's like, oh, it's just my hobby in the evening, so why should I come up to give a talk? But just because I think of his normal everyday job, he seems to be incredibly good at anything that involves floating point numbers. This guy. So NTL, the number theory library, and other libraries, Jabaro and so on, they all have funny names. For algebraic geometry, we include Singular, that's part of Sage, and one of the Sage developers, Martin Albrecht, wrote a C library interface to Singular, which allows us to do very, very fast multivariate polynomial arithmetic in Sage. In some cases, for example, over finite fields, I think it's the fastest you can get anywhere. In Macaulay 2, you can build it as an optional package, and then there's a bunch of number theory things, Perry, MW rank, and so on are all contained in Sage. Mike Rubenstein, who does a lot of L functions calculations, his code's in Sage, etc. There's a library that Eric Malthofen started called Linbox, and that's in Sage. It does a lot of very fast exact linear algebra. We have graphics. We use Matplotlib, which is kind of the numerical Python people. There's a whole community of numerical people who use Python. They use Matplotlib a lot. Matplotlib provides a MATLAB-like interface to plotting. It's very, very similar to MATLAB. But in Sage, because of the kind of more algebraic nature of Sage, or at least of the Sage developers, we've written a very Mathematica-like interface to plotting that behind the scenes uses Matplotlib. If you want a MATLAB-like interface, you can also use it. There's some 3D graphics in Sage also. And for group theory, Sage includes GAP. And Sage has a lot of numerical functionality because it includes GSL, the GNU Scientific Library, which is a C library for numerical computations, SciPy and NumPy, which are really the two big numerical libraries for Python. So there's a bunch of stuff in there. Now I'm just going to tell you a few shortcomings of Sage and a few advantages of Sage, and then show you a demo. Okay, that's the rest of my talk. So there's some shortcomings. The first and most, really the biggest shortcoming, but one that you could help with, is that Sage has probably less than 1,000 users. There really aren't enough users. Sage has, it's new, and so there are many bugs. And if we had, say, 100,000 users instead of 1,000 users, and they reported bugs, at least we'd know about all the bugs. And there are a bunch of people who are really good at fixing the bugs now. So the more bugs we know about, the better. In fact, we have a really good system for organizing the bugs we know about, and we have a bug day where about 10 people meet on IRC or in a room in University of Washington, just spend the entire day fixing as many bugs as possible. It's very productive. But still, we need a lot more users in order to find all the bugs. We really don't want to have bugs. It's really annoying when there are bugs. Personally, it's annoying to me because I do programming part of the time, and then I just stop thinking about programming and I do research. And when I do research, I don't think like a programmer at all. And if I run into a bug then, it really annoys me because I don't want to have to stop and think about a stupid bug. I want to do my research. So I really want Sage to have way less bugs. I don't think it's robust enough, at least for my taste. Meaning if you hit Control-C, it should always just stop. It shouldn't keep running, that sort of thing. Or you shouldn't be able to throw funny input at it that causes things to get messed up. And in some cases, it's much slower than some of the other commercial alternatives. There are hundreds and hundreds of people who get paid a lot of money full-time to develop Magma, Mathematica, Maple, and MATLAB, so it's hard to compete with them, but we're doing a good job, and I'll show you some examples later. But there's still many cases where these other systems can be much faster. And finally, it just doesn't do everything I want. Nothing does, but that's a big shortcoming. And you can fill in your name here. So it doesn't do everything you want. I guarantee it doesn't do everything you want. But probably, for you, no math software does everything you want. Some advantages. Sage is the only general-purpose mathematical software system that uses a standard language. Every other general-purpose system makes up its own language. And this has all kinds of implications. So with Sage, you're using a language. When you use Sage, you use the Python language. This is a language that has millions of users and is being developed by quite a large group of people who know what they're doing. And it's been tested. It's used regularly by Google and all these other companies. It's a language that can basically tackle almost any problem and has done so in many cases. So it's a really serious language. It has its little quirks from a mathematical point of view, but when you start doing something that maybe combines math with something else like biology or just sort of internet type things, then you discover that you're really happy you're using Python because somebody's already done something in the other area and they maybe spent a lot of time doing it. So you just get to pick from that. There's so many libraries that are available. Sage certainly has more functionality out of the box than any other open source math software. So if you decide you're going to use open source math software, then you're going to want to look at Sage. The reason is because it just incorporates all the other open source math software. So it's just kind of tautologically true. There are a couple of systems that aren't in Sage, but most of the really big ones are. It has a very active, well-rounded developer community. There's a mailing list for developers which has over 200 subscribers. And if you look at the number of people, distinct people who get their patches into Sage per month, it's roughly about 30. So people come and go, but there's really a lot of people working on Sage. Not nearly enough, but a lot. And the development is done in the open. So if you wonder how a decision's being made or something, you can take part in it, you get to see it, it's all archived. For example, just to switch to my email right now, here's my email right now. So the top line is a bunch of testing of the alpha release of the next version of Sage. This line is a suggestion for a change in how you get a monomial from a multivariate polynomial. So there's a huge discussion going on. People are voting and deciding on, how should that work? What should the notation be, and so on. It's something that a lot of people care about, and it's really confusing. There's really a lot of funny things that happen when you think about a multivariate polynomial and getting various monomials out. Or not just monomials, but maybe you have a multivariate polynomial and you want to factor y out and get the rest. Like what's the coefficient of y, for example. Other code so it's just this is just from the last few hours, but it's a lot of discussion by Sage developers. This is some stuff about organizing the next conference. But the thing to take away from that is that the development's done very much in the open. You can just look at it. All the bugs, if you want to know what the bugs are in Sage, they're listed at the bug tracker. And you can say view tickets, active tickets, and you'll see the things we haven't resolved yet. And it's just a list of all the bugs. So it's like Firefox or something where the bugs are all visible, publicly visible. And you can just log in and make comments on the bugs if you want, et cetera, et cetera. So you can see all these things. We use Track, which is a very nice system for tracking projects. There's also, there's a web page, of course, right here. Here's the Sage web page. The URL is sagemath.org. And there it is. So you can download any version of Sage that's ever been released, which is nice, if you look at the source code section at least. So for example, if you wrote a paper that used Sage, you could say, I use Sage version 2.8.3, and at least in the worst case, the person reading your paper could get that exact version if they're having some trouble using your code in a new version of Sage. But of course, if that happened, they would email the mailing list.
Does Sage include like Maxima in the source code?
Yes.
Or do you install that?
No, everything Sage needs is included right there. So if you look at this, the source code tarball is huge. It's 150 megabytes, and in that 150 megabytes, you have let's see. I'll go to the components of Sage for developers components. So basically, this is every single thing listed here is included standard in that Sage tarball. So when you download the tarball and type make, it builds everything that's listed right there. So it's really quite a range. So if you're interested in lattice polytopes, there's an incredibly good C program for computing with them, plus a Python interface to it that's included in Sage. Maxima is included in Sage, Pari, Linbox. If you try to build any of these Linbox without Sage, it's often very painful, but if you just build Sage, you got it. Et cetera, et cetera. There's a lot of stuff.
How is the Windows? You keep saying makes, that's under Linux.
So so let me make a few comments about if you actually want to use Sage. So first, building Sage from source is mainly something you would do if you really want to modify various parts of Sage. There are binaries that are available for various systems. So if you use Mac OS X, for example, there are binaries that are pre-built for that system. So you don't have to build from source if you don't want to. For Windows, since most of if you think about the mathematicians and the open source math software they've made, they all target Linux or maybe Mac OS X. So the support for Windows is very bad, in the sense that, I mean, if you just look out there what people have actually done in a non-commercial context, it's almost never for Windows. So what we're currently doing, and I don't know how long we'll do this, we currently provide a pre-made VMware image. So you download this file, you unzip it, you download the free VMware player from the VMware website, and then you can double click on an icon, and then the program runs. Then you type the word notebook into that program, and you use your web browser under Windows to use Sage, use the Sage notebook. So use your Windows web browser, but there's a little text window sitting there which actually provides all the functionality. So in other words, there's a version of Linux that's free that runs on your computer, and that actually does Sage. We did have a Cygwin version for a while, but we actually found the performance of VMware with Linux installed into it was better for a lot of what we were doing. So that's what we're currently doing. We do have plans and thoughts about making a completely native Windows port, but that won't happen until we have more money, which we may or may not ever have. It's unclear. I'll have a slide about that in a minute. But this is actually very easy to install. The instructions are right here. So you just download the file, you extract it using zip, then you download that free program VMware player, and then you double click and you run in Sage. So you don't have to build anything on any of the standard popular operating systems. The one OS that we don't quite support that you might want is Solaris, and we're working very hard on getting full support for Solaris. But the problem is, again, most developers these days don't target Solaris, so there are a lot of little problems. Okay, so let's get back to the talk. I think I'll just skip this, skip that, and just the URLs again. And I think I'll just skip to the live demo. So, just a second.
Can I
Sure.
ask you quick? If you go back to where it says sagenv.org,
Yes.
what are those?
I'll show you. So if you, so does this look familiar to anybody? Does it kind of look like something familiar? Like the login page for Gmail? So it's not the login page for Gmail, it's actually a login page for the Sage Notebook, which this is something anybody can just use. You just go to sagenv.org, and as long as you're using, it doesn't work so well with Internet Explorer. It works fine with Firefox and Safari and so on. But you can create an account by clicking sign up for a new account. You can then log in. And this is running at the University of Washington on a computer that I have there. Actually a very powerful computer, a famous computer. It's running on the computer that did the E8 calculation that was in all the news, the so-called Sage supercomputer. So if you use this sagenv.org, you're using that computer. So, so this is the Sage notebook, by the way. It looks a lot like Google Documents, except it's for math. And might be slow, I'm not sure about my network connection. But you click and then it brings up the notebook or the worksheet that you're interested in. So that's what, okay, so here it is. So that's what sagenv.org is. So this is an example of actual stuff. But I was just, I mean, this particular worksheet, somebody asked how to do something, so I just did it, and then I clicked publish, and then pointed them to the resulting published worksheet. So you can kind of think of it as, it's kind of like Google Documents, but for math. All right, so now let me show you the live demo. It's right here. So I'm going to use Sage to do some very hard calculations, such as 2 plus 2. So what you do is you type in the input in a cell. You can make new cells by just going like that. Actually, somebody wrote on the mail list they're shocked and amazed by how quickly Sage can compute 5 to the 5 to the 5 for some reason. But, so you type in input and then you hit Shift-Enter, which is like Mathematica. Now here's an example of summing integers up to 100, multiplying pi and e, computing a numerical. I redefined n below for an example I was showing somebody before the talk, so I have to reset it to its default value. N is a function that gives you a numerical approximation for something. But of course, if you overload it with something else, then it's not going to work like that anymore. Here's an example of calling the n function, but It's like the Mathematica capital N, but it's lowercase n. So getting a numerical approximation for pi times e. You can also call using functional notation like that. I mean, like object-oriented notation, not functional notation. All right, here's an example that's kind of interesting. So
Does the combo notation work too?
the what notation?
Like the Mathematica, or what did you add?
No, we haven't implemented that, or I'm not sure if we should. But basically, you can type anything or make any object and then do dot, and then there are various methods you can call on it. And in fact, you can use tab completion, which is very nice. Like if you set z to be pi times e, let me do that up here. So if you set z to be pi times e, you could do z dot tab, and it shows you all functions that it makes sense to use on that object. And one of them is n. And if you start calling it and then hit the tab key, you'll see the help for that function. So a lot of the people that worked on this graphical interface were undergraduates who used IDEs like Visual Studio and so on. So they wanted the same sorts of features in here. There's also nice features like you can, if you're making a block of code, you want to indent it, you can just hit tab and indent the whole thing, or unindent the whole thing, which is nice. Whoops. So it's kind of cool because you have this sort of graphical way of working with Sage. You can actually work with a whole bunch of different languages. Here, it's in Sage mode right now, but this is a list of the different systems that are supported. So you can switch to, you can actually do list. So you type in list in a block and it gives you the output. And it runs one copy of an interpreter. It's not a different thing for each cell or something stupid like that. And it's very robust as far as starting up calculations and then interrupting them by hitting escape or clicking the interrupt button. You can set it to all these different modes. Like if you know about the GP system, you can change it so that everything is evaluated using GP. So you can do GP commands. So I made an elliptic curve in peri GP. So it provides a graphical interface to really almost all math software. Let me show you another kind of interesting example that we wrote recently in response to what some numerical people, what did I do?
GP.
Oh, it's in GP mode, thank you. I better switch back to Sage. Otherwise it won't work. Oop, not Axiom. Sage mode. Sage mode, okay. Yeah, GP doesn't evaluate. Maybe I didn't. Okay, switch to GP and then switch back to Sage. Hopefully it's now Sage. Yep. So right there where I hit Shift Enter, it takes this Fortran code, it parses it using something called Weave, which was developed by numerical people. It figures out what the functions are that are defined in here. It then runs a Fortran compiler on the code, and then finally it imports the result into Sage so that you can use it, which is what I'll do next. Right here. So this line right here, what it did was, there's some like boilerplate that's needed because the interface that you get to Fortran code requires using NumPy in some cases. What it did is it computed the first 10 Fibonacci numbers using Fortran. And you can see the actual output right here. And if you wanted more of them, you can maybe do 100. Fortran's pretty fast at computing floating point approximations to Fibonacci numbers. So it's actually like a GUI for Fortran, if you like, and a lot of other programs. So you can see how this could be useful in some courses. Here's an example of drawing a plot of sine of x squared from minus pi to pi. Could be brave and do sine of x cubed. See what happens. Okay. So you can draw plots. You can do arithmetic with plots, which is kind of cool. So make plots P1 and P2, then add them together, and that combines the two plots, and then you can plot the result. You can also, given a plot, a graphics object, you can save it to a whole bunch of different formats, including PDF format, EPS format, and so on. So you can embed the result as vector graphics. I mean, these things are PNG images, so you can just right-click and save image as. But it's also nice to be able to have a vector graphic for your paper or something. There's a lot of graph theory functionality in Sage. The graph theory is kind of an interesting thing. So two University of Washington students and a guy who just graduated from BYU, have done most of the work on the graph theory. But the graph theory builds on a package called Network X, which has been developed for the last couple of years in Python by people at Los Alamos. So we include Network X in Sage and then wrote a massive amount of additional code on top of that. So this is an example of creating a graph and then plotting it. We have an isomorphism tester that's the first open source isomorphism tester ever. So there's something called Naughty, but the license is really weird, and it's not GPL compatible. It doesn't fall under the open source definition. In other words, you can't use it if you happen to do anything for the military, that sort of thing. So we wrote from scratch a much more readable version of the same algorithm that Naughty implements, where we is Robert Miller. So he's a grad student at the University of Washington. Here's an example of drawing a graph of a graph in 3D. And if you look closely, you'll see that there are little shadows and nice reflections and so on. It's done using a ray tracer that's included in Sage, called Tachyon 3D. The ray tracer is used as a backend for a lot of molecular imaging by some guy named John Hunter, and we include it in Sage and use it for lots of 3D graphics that look pretty. Here's a graph of an octahedron, or I mean a cosahedron, sorry. Here's some examples of symbolic integration. I showed you some earlier. Notice that if I use the show command, then the output gets typeset. And this is a very interesting thing. What it does is it uses JS Math, which is included in Sage, well, JS Math is a complete implementation of the tech layout engine in JavaScript. So it doesn't use like open math or any math-ML type thing. It's just you just take the LaTeX expression and then typesets it right there in your web browser. It's pretty amazing. Here's an example. I'll compute a random matrix and invert it to random 5x5 matrix, and then plot it using JS Math, or typeset it using JS Math, and compute its characteristic polynomial. And actually, the algorithms behind the scenes here for char poly and inverse and stuff are really sophisticated. They're not just like silly algorithms that would work for much bigger matrices. Here's an example. If you have any object at all in all of Sage, if you say LaTeX of it, it outputs a print representation of that object that you can paste into your paper. Even works with, say, power series, which is nice. So it can save you a lot of time. Instead of having to try to format it for your paper, you just put it in Sage and you get it out in LaTeX for you. So if I took the same thing and said show, I would see the typeset version. But you can also get the LaTeX version. And when if you define your own objects, you can define a LaTeX method for them and LaTeX them. Here's an example starting to show you some of the things that are really fast in Sage. There's a guy named Gregory Bard and a developer, Martin Albrecht, who have written a very, very fast algorithm, or they've come up with and implemented a very, very fast algorithm for dense mod-2 linear algebra, which asymptotically is slower than these sort of very fast, asymptotically fast algorithms, but up to about 10,000 by 10,000, it's the fastest thing in the world for dense linear algebra. So here's an example. I just took a 5,000 by 5,000 matrix over F2 and squared it, and it took less than a second. And I can compute its echelon form in 0.3 or 0.44 seconds. So if you ever want to do mod-2 linear algebra from a dense case quickly, this program is very, very good at that sort of thing. And it's only available in this system. Here's an example of echelonizing a rather big matrix. Here's another example with a 200 by 200 matrix of size n by n plus 1. Sage can echelonize it. Really, it's calling something called IML, which is a very, very fast solver for integer systems. But we came up with a little algorithm that turns the output of IML into echelon form. And it can do this echelon in 2 seconds, whereas Magma, which is really the fastest at dense echelon, otherwise it takes almost 70 seconds. So in some cases, Sage is way, way faster. But you can also come up with examples that are the other way around. Though Sage, its exact linear algebra is being built on top of LinBox now, and LinBox is a big project that's getting better and better. Here's an example of Sage interfacing with Mathematica. So I create pi over 3 in Mathematica, and then I could show it. This calls Mathematica's LaTeX expression method, and then displays the result. And you can call methods. So this A It's a Python object that points to something that lives in a single instance of the Mathematica interpreter. So that's what that A is. So you could do arithmetic with it, you could call any Mathematica function on it, but it looks like you're using Python. So you can benefit from a lot of functionality in Mathematica if you have it. And this sort of situation where you have this Python object, A, that wraps something in another system, works for a whole bunch of other systems. It's not just a Mathematica thing. It works exactly the same way in all the other systems. That looks funny. So if I do percent Mathematica, that allows me to just type code directly into Mathematica. Here's an example that's kind of amusing. So in the Mathematica book, or the Mathematica tour, on page 6, they talk about a frontier computation in number theory, namely computing the number of partitions of 10 to the 9th. And then they say Mathematica can do it in seconds. So I timed Mathematica. To do 10 to the 9th takes about around 60 seconds in Mathematica. And in Sage or Magma, the two sort of number theory systems, if you like, at least I view them as very capable in number theory, it would take forever. I mean, they couldn't even get anywhere near 10 to the 9th. They're very, very slow. Mathematica is far faster than absolutely anything else out there. So I posted this on a mailing list, and then about 60 responses followed, along with some very fast C code. And now Sage can do it about twice as fast as Mathematica. So probably in about 10 seconds out there, this 34 seconds for doing 10 to the 9th. If I do it with Mathematica here, it'll take, actually I timed it earlier, and it takes, let's see, it takes exactly, on this machine, 55.9 seconds. So something went, I mean, I didn't do anything, I just said, it doesn't work well, and then a whole bunch of people discussed it, and suddenly there's really, really good code for this. It's really cool. And the code's beautifully documented too, which is nice. Here's an example of working with elliptic curves, which are one of the main objects of interest to me in my research. Here's an example of plotting an elliptic curve over a finite field. Just kind of looks random. And counting points. And my last example is deriving the quadratic formula using Sage. Behind the scenes is actually calling maximum. And here's an example of doing the same in Mathematica. And here's an example of deriving the formula for root of a general cubic, or almost general cubic. Okay, so I now have, I think, looks like, well, my watch says 2 minutes left, and I've completely finished my talk, so I just invite you to ask questions or make comments for the remaining 2 minutes.
Thanks, Art.
Yes?
What kind of thinking did you go through to pick Python? I remember when I first saw Python in 1999, I thought, well, there's invisible characters here which have important meaning, so I kind of shied away, but I guess that hasn't been.
I mean, so in Python, if you write for I in range 10, and then you indent, that's how you indicate the stuff that's in the for loop. And in other languages, most other languages like C, what you do is the following. You write for, something that determines the loop, and you write the code, and then you stupidly add a print statement and forget to put braces, and you end up with a bug because it looks one way, but the logic's another way. So in fact, I think that the fact that indentation in Python is significant is one of the biggest pluses to Python, because it means that when you look at somebody else's code, the indentation doesn't mislead you and confuse you about the logic of the code. It also means the code is much cleaner. Instead of having semicolons and begins and ends and braces everywhere, they're just all deleted. So the end result is cleaner, easier to look at code with less symbols, and it's easier to read. And in choosing Python, readability for me was a much, much more important criterion than writability. So, and in fact, when you have a big project with a lot of people working on it, if other people can't read the code, then it's going to just die, and or you'll have to pay them more. And since I'm not paying, I barely pay anything, whatever I can scrap together, the code has to be readable, so other people can really join in easily. And especially for a volunteer project where a lot of people kind of do it every once in a while when they have time. So that was one thing, but there's a lot of other reasons why Python is the right choice for this particular project. I mean, it's an open source system. It's designed from the start to be a gluing language to pull together lots of other things. I think that for the same reasons Google and Industrial Light, the people that do Star Wars, etc., choose Python. I think it's the right choice for Sage. It's readable code, good for very, very large projects, and it's and it has the ability of writing the compiled version is very, very important. You can't write a serious system if it's all interpreted. Okay, more questions in the back?
I just had a question, especially as you go forward and get more and more developers, and you
Yep.
start to write more actual software rather than just gluing together a bunch
Yep.
of software. What kind of assurances do you have in place to make sure that when people write bugs, they don't necessarily find their way into the system and subsequently into somebody else's?
You never know for sure, of course,
sure.
with any system. We do have something called JSage, which is, in other words, we set things up kind of like a journal. It's the site. So we have refereed code, especially for new people. But we referee the code a lot. So when patches come in, people look at them, and I almost never look at something unless somebody else has looked it over and decided that it's good. And there's a specific core group of people who really know the system well that look at anything questionable who are listed here. They're actually all grad students, interestingly. But they've sort of put in the most effort. So we have, it's just like with a journal, basically. Plus we have a huge number of automated tests. So if you change something in the code here and it slows something down a lot or breaks something else, we'll know. We in fact have, I think, over 20,000 lines of input tests. And it's all automatically tested constantly, and you verify that the output agrees with what's claimed and that things run. So we do a lot of automated testing. But at the end of the day, certainly bugs do sneak in. And then the best thing of all is if there's more Sage users, so there are more people to spot the bugs and report them. You had a comment?
I had a question. So does Sage have Grosvenor bases and
Yes.
or algebras?
It has Grosvenor bases, yes, singular, but you see it in Sage. You can create an ideal and create quotients of rings by ideals, and the calculations behind the scenes are done with Grosvenor bases. Looks like everybody's getting ready to go, so if there are any other questions or comments, just come and talk to me outside after the talk, okay?
Sorry, I thought we actually had
Oh, well, people are getting up, so it's yeah. Well, I don't have any good stuff.
I'm just wondering if the specs of the machine is.
2.33 gigahertz cores for the.
Yeah, it's basically the same as mine.
Yeah.
Can you do it 5,000 by 5,000?
I'm using which is actually not fast.
I'm using only 10 direct,
Yeah.
but
It's actually
still in CCS, cosine CCS.
You can say generate the random matrix.
Just to
Yeah?
the,
Oh, I didn't know that. Sure.
I'm using a
people
yeah, I'm not using it directly. I use VMware. I use VMware.
yeah,
I'm not
CCS, you don't have it.
Yeah, we're still making
yeah,
I know what's the top
Have you used
directly on that.
I was on the chocolate.
I would just run with the install VMware by because the West is for all the hardware. Because of the VTX
meeting between San and half the people
the
are
virtualization.
about 14.7 of them were former about that.
Whereas
And Steve, there,
sorry,
complaining about
it is not there exists a Debian package, but it's not really maintained. So it's really just get the, but there's a Debian source.
Well, I guess,
If you go to the download page, I build Debian binaries.
when it's a brand new
Really
video.
type it, and then there's Debian. So all you do is just download, you get the newest one. Yeah, it's 64-bit. And you can also build it, I mean, it's easy to build on Debian, but here's a binary build for And what I do is I install a little version of Debian, then I just build the thing. Great, you can build it from source. If you use the Target, all you need to build from source is
I ran into
GCC,
Mahoney a long
like a
time.
few very basic things. Or you can just hit the
I think they
tarball,
use it.
extract it, and then just go into the directory and you type /sage.
Well, good to see you.
Yeah, good to see you again.
Take care.
Is there some kind of way
Yeah, there's
to
actually-
import these commands?
Oh.
So,
I don't know, it depends on the.
Very much.
Probably, yeah, there's no, basically you're asking for something that automatically converts code.
Not necessarily, but some way for them. See, I'm very excited about open source.
Right.
And
There's another
almost all of
book.
them, they have a site license at our university.
So is this like crypto, like stream ciphers, all this sort of thing? Or
No,
is it-
it's
or
very
is it
basic
other-
introductory
Yeah, but
stuff.
that's, I mean, stream ciphers. So
Oh,
there's
right.
one of the Sage developers, David Cole, who worked for the Magma Group for like 10 years, just isn't working with them anymore. Sorry to not answer your question.
Well, that's cool, I'll ask you later.
Okay, cool, fine. He wrote a cryptography book which uses Sage throughout, and it's free. So you could look at, you could take a look at that. He teaches cryptography a lot, and he had written a book that used Magma throughout for all the cryptography stuff, and then he rewrote it into Sage. And then he also implemented a lot of crypto stuff. So Sage also has PyCrypto, which is implements all the standard ciphers in crypto. And then
Maybe
David
it'll
Cole
be
implemented
used
a
to
bunch
compute
too, for
things like
education
finite
purposes.
field
But yeah, finite fields
and
are
RSA.
finite fields are extremely good in Sage already. At least some of them. Very large finite fields aren't as optimized as Macron, but small ones are
There's
really
a
good.
help documentation. I'm sure
Yeah, there's a 2,200 page. Oh, well, not how,
Well, I mean, if there's commands in mathematics or stuff like that, no.
you're gonna have to learn. I mean, I have no idea how you compute a finite field in Mathematica. And
It's really not the sort of thing that sort of package is designed for. really.
yeah, it sucks at that. I mean, it's way easier in Sage, like right off to do that sort of like algebraic stuff. Is, to make a finite field, all you do in Sage is you just say k equals g top. So you want a finite field of order what? 2 to the 8. So you give the name of the generator, then you give a finite field. And there's a 2,000 page reference. You should take a look at it.